Hello class, in today's lesson we are going to talk about binary search, an important tool for us in finding data and looking for data in the fastest way possible, and also an important algorithm that you need to understand for the multiple choice section of the AP exam. Let's take a look. So here we have two sets of data. First, we're going to look at the left-hand side set of data with these different column heights, and it's out of order. And we don't really care what the column heights mean. We just know that their value is different based on their height. And as we move across, we have different indexes. Now let's say we want to find a column of height of whatever this green column is here. If I want to find a column of a similar height within my first data set here over on the left, I'm going to have to use a brute force technique. I'm going to have to take my column and one at a time compare it to each one of the columns, one by one, going through, and it's going to take a moment until I can finally find, there's one that's about the same height right there. We'll call it close enough. I've now found my search term. But it's going to take a while. And my search term could end up going all the way to the end here without finding it. And it could be very slow for me to find this search term, especially if we imagine a large data set. And if we remember our big O notation and our algorithm analysis, finding something in an unordered data set like this would take O of n in our worst case, because we would have to go all the way through. Every single n number of elements would have to be checked. Very inefficient. We always want to do better. Now let's imagine that we have over here an ordered set. If we have an ordered set of data, if I want to search, I could use the same technique. I could go through one at a time, searching 1, 2, 3, 4, 5, 6, 7, 8, and there's 9 times. That's a lot of searches, though, to find it. And again, maybe I could get all the way to the end of the set and not find it. So how can I reduce this number of search terms? Well, since it's an ordered set, it already has a fair amount of coded information into it. So if I think about, instead of searching the entire thing, we know that somewhere in the middle, right, this search term is both, whoops, wrong one. This search term here, come on now, behave. This search term is taller than the shortest value, and it's also shorter than the tallest value. So somewhere in the middle, somewhere in there, there must be a value that's at least close to this value. So what can I do? Well, I can split the data in half. So if I split the data in half, and then I check my square, my column against that column, and I make an observation. I see that the column that is there versus the one I'm searching for is shorter. And since the column that is there is shorter than the one I'm searching for, and I know that this is an ordered set, I can immediately see that everything to the left of our current position, I don't have to search, because it's going to, by definition, be shorter than my search term. Well, this is great. I've just cut off half of my searching items. I can now do that again. What if I do that again? I split everything in half again. I now take my green square, my search term, and I now search for it. Bingo, bango, I found it. Wonderful. Now, it only took me 2 comparisons. This is number 1, and that's number 2, compared to 9 comparisons that it took to find it before. This is a huge improvement in efficiency. And if we think about it, every time splitting something in half means that we're reducing it essentially by a power of 2. So the number of times that we have to search this gets reduced in half each time we split it, which means, if you remember your math class, that this is going to be O of log n. It'll be log base 2 of n. But when we do big O notation, we leave out the 2. So this is O of log n, which is very close to being, or about as close as we can get to being O of 1. Very, very fast. Even a huge data set can be searched in a very, very short amount of time with very few search parameters or number of times doing comparisons using binary search. So this is binary search. So what does it look like when we define it? Well, we define it fairly simply. We're going to define it as find the middle of your data set. So it's a fairly simple process. Find the middle of the data set. This is number one. Find the middle and compare it. Once we compare it, if the data set to the left, or if our search term is smaller than what we've looked at, then we need to look to the left. So if our search is smaller than our data, then we're going to want to look from 0th position to our midpoint. That's where we search. We search from the 0 point to the midpoint. And actually we search in 0 point to midpoint minus 1, since we already searched the midpoint, right? So this is our middle. We find the middle mid, and we search from 0 to mid. Now, if our search term is, let's use purple here. If our search term is larger than the data we found, then we're going to search from the mid plus 1 to the end of our search area. Now I should redefine this 0 to mean the beginning of our search area. And the reason being that we don't necessarily have to search from 0. Our search area could be between two different areas. So it could be between these two spots. This could be our search area right here. So the middle could be our beginning, right? Just as I said, middle plus 1 to end is our search in this way. So our middle doesn't or our beginning doesn't necessarily have to be 0. Once we find these two things, we repeat the search. In the new area. Okay, can you see how this is recursive? We are breaking down the problem into smaller and smaller and smaller chunks, passing a smaller portion of the array into our recurring method call each time. If we get to a spot, and finally here, if we get to a spot where our two data points are the same, then we return we haven't found it. So if we find that our midpoint is greater than or equal to our end, we return -1, right? Not found. All right, let's take a look at this in the Repl.it. This Repl.it, of course, is linked down below. Here it is. So we actually worked slightly backwards. So if beginning is less than or equal to end, so as long as our beginning term is the same as our ending term, we're going to continue. So as long as our front isn't in front of our back. Then we find the midpoint right here. So we find the midpoint. This is step 1. Then we check if we found our search term. If we found our search term, hooray, wonderful. We're done. Go back to return this value. We're all good. Now here comes the magic part. These 3 lines right here are the magic. So if our middle point, if the data we're finding is larger than our search term, so if our data is larger than our search term, that means that we have to search in the beginning of the list. It means our data is bigger, and we have to search the beginning of the list. So what do we pass? Well, we pass in, we call binary search again, we pass the array that we have, we pass in our same search term, and now we do beginning here, and our midpoint minus 1. However, if our midpoint is smaller than our search term, we skip this first return statement, we go to the second one on line 17 here, and we pass in, we search to the right, searching our midpoint plus 1 to the end. And we see this recursive call going all the way down until we either find it, so this is going to be found, and this will be not found. This will return the index of any value that we can find within an ordered set. And this is, again, important. We must have an ordered set required. I'm going to put this in big letters over here. Must have ordered data. Advantages, this is super fast. It is fairly elegant in its execution, but it can be a little tricky to understand the first time through. Take a look at this Repl.it, start to play around with it. You can play with the search terms right here. So here's our searching term, 99. We begin at 0, and we see that we initially pass in 0 to array.length, so we're searching the entire array. We can change these parameters to search just a section of the array if we want to. So feel free to open this up in Repl.it, play around with it, and see what the code does. Play around with some of these terms. You won't break anything. You can always reset things too in Repl.it or refork it later if you are interested. So that is our binary search. In the next lecture, we're going to talk about using binary search, or a cousin of binary search, splitting data in half to now sort it for us in a much faster sorting algorithm than we've seen before. Thanks for watching. I'll see you in the next one.